Hi, everybody, and welcome back for Unit 5, Lesson 10, which is our introduction to something called optimization. Now, when you hear the word optimization, you should think of the word optimal or best. So, optimization comes from the word optimal. And that word means that we're trying to find the best way to do something. Now, that might mean that we're trying to find the maximum of something, so the most I can sell, or it might mean we're trying to find the least of something, the least amount of money I can spend. But we're always trying to kind of find the best way to answer our question. Today, we're going to have two learning targets. I can use a derivative to find a maximum or a minimum value for a function on a given interval. So we're going to be finding maximums and minimums, which makes sense because maximums and minimums are high points and low points. So they're oftentimes the best or the worst way to do something when our function represents a real world scenario. And this is the second learning target for today is I can interpret the meaning of maximums and minimum values in specific contexts. So, what that tells you is that today is all going to be about applying the ideas that we already know about maximums and minimums, but in a specific context or story scenario. So, here's our introduction. Suppose a farmer has 100 meters of fencing to build a corral against one wall of his barn. The images below show a few options for pens that use 100 meters of fencing. Find the area of each of these options. And we're also going to list the amount of fencing used. So for option number one here, the amount of fencing would be 25 plus 25 plus 50. And 25 plus 25 plus 50 would be 100. So we are using 100 meters of fencing here. Now, to find the area that's enclosed, we would find the area of the rectangle. And an area of a rectangle is going to be length times width or base times height, whichever kind of words you prefer, it doesn't really matter. Which means here I would get 1,250 meters squared are enclosed within this rectangle. For option number two, we're going to use 40 plus 40 plus 20 meters of fencing. So if we add those up, 40 plus 40 plus 20 would be, we're still using 100 meters of fencing. The enclosed area here would be base times height, which is 40 times 20. So that would be 800. So even though we used the same amount of fencing as we did in the first option, we enclosed a smaller area because of the dimensions that we chose. Last but not least, let's try 10 by 10 by 80. So the amount of fencing I use here would be 10 plus 10 plus 80, which is 100 meters. So we're using the same amount of fencing, but the enclosed area here would be 10 times 80, which would be 800. Once again, I used the same amount of fencing, but I enclosed a smaller area than I originally had here, and I enclosed the same amount of area, but just in a different kind of shape as I did here. Do you think, first of all, that these are the only possible sizes of corrals that can be made with 100 meters of fencing? I'm going to tell you right now, these are not the only sizes that could be made. For example, you could make a corral against a wall that uses 20 meters of fencing here, 20 meters of fencing here, and 60 meters of fencing here. There are lots and lots of different sized options that all use 100 meters of fencing. Next, write an equation that will give you the area of any corral that the farmer builds that uses 100 meters of fencing. Now, because we want to write an equation for the area of any corral, we need to kind of use variables here to represent the size because this has to represent the size of any area. Now, if I sketch a picture of what's happening here, we've got our wall and we're going to build our corral. Now we're going to make it any size that we want. This is a really bad rectangle, I apologize. There we go. We're going to make it any size that we want. Let's call kind of the height of our rectangle y. And let's call the width of our rectangle x. Now we know that all together, those three sides need to add up to 100. So that means that I already know that 2y plus 1x has to equal 100 meters of fencing, because that's how much fencing I have. I also know that the area of this rectangle is always going to be x times y. Now, when I write this kind of equation, I often want to make sure that I only have one variable in the equation. And since I'm trying to find the biggest area possible, I want to make sure that this equation for area only has one variable. Unfortunately, right now it has an x and a y. So, one of the kind of interesting techniques that we use a lot of times in mathematics is we substitute. So, we solve this equation where we have a number that we're equal to, that we're set in stone. We know that this is always 100, and we solve it for one of the variables. Doing a little bit of rearranging here, I would figure out that x would be equal to 100 minus 2y. Now I can take this equation and substitute it into this area equation. By doing that, I get area equals, instead of x, I'm going to fill in 100 minus 2y times y. And now I have an area equation for the area of any corral that I want to build that I could use no matter what. That only uses one variable, which is kind of what I wanted here. Now, why would we do that? Well, we know that there are like a lot of different options for sizes of corrals that we could build. How could we guarantee that we make the corral that has the largest possible area? And when I say largest possible area, I mean you know for sure that you've got the biggest space you could possibly have, and that it's guaranteed that that's the biggest. Well, this is where using a derivative or optimization is really helpful. If we can write an equation for area and we find the maximum value because we want the largest, then we're going to know for sure that mathematically that's the biggest corral we can build. So let's go back to how we wrote this equation. If you sketch a picture, which we did on the other page, we labeled in that picture using variables. And the reason we used variables here is because we know that we want to make it the biggest possible. We don't know the exact dimensions to use, so we can't use numbers. We can only use variables. Now, we also know a little bit of something extra. We know that the perimeter of this fence, so 2y plus x, if you were to add up all that fencing, it's got to be 100. So that's kind of set in stone. It's a known quantity. We also know that we want to find the maximum area, which means we're going to need a formula for area. So my area here, my area formula would be x times y. But in order to find a maximum, we're going to need to take a derivative, which means we kind of only want to have one variable. So what we're going to do is rearrange this equation. We're just going to subtract the 2y and then substitute it into the area equation so that our new area equation only has one variable, which is 100 minus 2y times the other y. Now, after you have your area formula, and we made our area formula only have one variable, the next step is to maximize that formula. Now, to find a maximum, we're going to take the derivative, set it equal to 0, and solve. So, before I take the derivative here, I can make my life a little bit easier by just distributing this y. So I would have 100y minus 2y squared. Now, the derivative would be 100 minus 4y, and we're going to make that equal to 0 to find the maximum value, which means 100 is equal to 4y, which means y is equal to 25. Now, once I know that y is 25, in this case 25 meters, I can substitute that back in over here to find x. So x would have to be 100 minus 2 times 25, so 100 minus 50, which is 50 meters. Now, the question said, what size corral should he build to make a corral with the largest possible area? So the size should be 25 meters by 50 meters. And that's going to give us the largest corral possible, guaranteed. Okay, this is kind of just an introduction to optimization, just to kind of get the idea of what's happening. That when we want to find the best way to do something, we can actually set up equations and use derivatives to help us find that so that we know for sure we've got the best possible option. Tomorrow, we're going to be doing kind of an investigation to examine this idea some more. And then in our next video, you'll actually get to see several more practice problems to kind of work through the process of how you might do this procedure in a variety of scenarios. Thank you guys so much for watching and have a wonderful afternoon. I'll see you soon for some practice.